Hello again. This is going to be the third of our lessons this week on projectiles, and in this lesson we're going to take all of the learning from the first two and introduce vectors. Now vectors you might be worried about, but I can tell you that they do make these questions easier. They simplify things down. Let's see why. So in this question, let's have a look at the similarities. We have well, the first sentence here, a fixed origin O is located on horizontal ground. Vectors I and J are unit vectors pointing horizontally and vertically. That's just defining what I and J are. We don't need that information really. A particle P is projected from the point A with position vector 7J. This means that A is 7 meters above the ground. The velocity is given as an I and J vector, 24I plus 7J meters per second. That's shown in the figure above. Now let's remind ourselves, when we did collisions of ships last week, when we had the velocity vector, that tells us the direction of movement. So forgetting for a second that this is a projectile, if something moves with a constant velocity of 24I plus 7J, that means that the object is going to move 24 meters to the right and 7 meters up every second. Okay, so we have its direction as well as its velocity. And from the velocity, we can find the speed. We could work out the magnitude of the speed using Pythagoras theorem. So then, now let's remember that this is a projectile. It doesn't follow this straight line path. It's going to follow a parabola. But this 24I plus 7J tells us the initial velocity. Now, not only that, the 24 is the horizontal velocity. We don't have to use sine and cosine for this. 7 is the vertical velocity. So let's put all that into practice then. Consequently, the particle is moving freely under gravity. That's standard. That's similar to what we've already worked on this week. Find the length of time for which P is at least 9.1 meters above ground. So in order to do this, I'm going to resolve vertically because we're talking about the height above ground. So S U V A T. We're getting so used to doing this now. So if the particle is 9.1 meters above ground, given that it was started life 7 meters above ground, then the displacement we're interested in from the point of projection is 2.1. It's already 7 meters above ground. It needs to go 2.1 meters more, and it will be 9.1 meters above ground. The initial velocity in the vertical direction is given by the J component of the vector, so it's just 7. The final velocity we're not interested in. The acceleration is minus 9.8 meters per second squared, and the time is actually what we're interested in. So let's use S equals ut plus half at squared. And we just substitute all the information in. 2.1 equals 7t minus 4.9t squared. Rearrange this into a lovely quadratic. And then we will use our calculators to solve. Again, you're not awarded marks for showing that you can complete the square or use the quadratic formula. You need to show that you're solving a quadratic equation equal to 0. After that, that's it. So we have 4.9t squared minus 7t plus 2.1, and we get two solutions for t. We get t is 0.4285, and we get t equals 1. So with these values of t, what do they actually mean? Well, the particle is being projected 7 meters from ground, so it's going to travel up until it gets to 9.1 meters. But now it seems that the particle is going to keep going up, and then it's going to come back down again through 9.1 meters above ground. So the time when it first goes through 9.1 meters above ground is 0.4285 seconds. The second time that it goes through 9.1 meters above ground is at 1 second. And so we can use those two values. So the time above 9.1 meters is just going to be given by 1 minus 0.4285, which is 0.5715, which is 0.57 seconds, correct to two significant figures. So for part B, this projectile is going to pass through the point with the position vector 48i plus 8aj. All right, so that means relative to O, it's going to be 48 meters to the right and a meters up. We need to work out what the height is at that point. Okay, so effectively we're being asked, when it's traveled 48 meters horizontally, what's its height? You might be thinking, how on earth do I go about that? But let's have a look. There's only two things we can do with projectiles. We can resolve things vertically and we can resolve things horizontally. And so let's have a quick look. So the displacement vertically then is actually what we're trying to work out. We're trying to work out its height at a given point in the projectile path. So we don't know what that height is. We know that its initial velocity vertically is 7. We don't know what its final velocity is. We know the acceleration is minus 9.8, and actually we don't know what the time is either. So we don't have a lot of information, not enough to go on. Okay, we'd need either the final velocity or the time to proceed with any calculations this way. So let's look at the only other thing we can do. We can resolve things horizontally and see how they come out. So horizontally, distance is speed multiplied by time. We know the horizontal distance, it's 48 meters. We know the initial speed horizontally, it's 24 meters per second. And that will allow us to calculate time. So 2 seconds after the projectile is projected, it's in this location. So now we know that t equals 2. So let's use s equals ut plus half at squared. So s is 7 multiplied by 2 minus 4.9 multiplied by 2 squared. So s is given by, let's work this out, minus 5.6 meters. Now, don't be worried about the negative. Let's go back to the diagram. If its displacement relative to where it started is minus 5.6, that just means it's 5.6 meters below the point where it started, talking about vertically. So it's down here somewhere. So if we're trying to find out how high above the ground this is, which is what this is, okay, this AJ part, this J component is the height above ground, because this is relative to O, then A is given by the 7 meters where it starts above ground, minus 5.6, which is 1.4. So the position vector of the particle at this point is actually 48I plus 1.4 J meters. Now that's it. The calculations are the same, but the vectors simplify velocity. Let's have a look at a second example. So another fairly standard projectiles question. A ball struck by a racket 2 meters above the horizontal ground. Immediately after being struck, the ball has this velocity, 5I plus 8J. And then we have our I's and J's defined for us. Then we've got the fact that the ball travels freely under gravity, and then it lands the ground at B. So far, so standard. Okay, you really should be spotting the patterns in these questions now. So find the greatest height above ground reached by the ball. This isn't the first time we've done this. So SUVAT, we want to find the displacement. Our initial velocity in the vertical direction is given by the J component of this vector, so it's 8. The final velocity is 0. Again, whenever we're trying to find the greatest height, the final velocity has to be 0 because it stops instantaneously before it starts to move back down again. A is minus 9.8. So we can use V squared equals U squared plus 2AS. So 0 is given by 8 squared minus 19.6S. And so S is going to be given by 64 divided by 19.6, which is 3.3 meters. Correct, two significant figures. Now that's the displacement above the point of projection, because this whole model here has been set up based on the point of projection. So the particle has traveled a further 3.3 meters into the air above ground after it was projected. So the height then is just going to be our 3.3 plus the 2 meters above ground when it started, which gives us 5.3 meters. So now we're being asked about the speed of the ball as it reaches B, and this is very similar again to a question that you were working on in previous lessons. If we're asked about the speed, it means we're going to have to find the magnitude of the velocity. So in order to do that, we need the horizontal velocity, which we're given in the question. It's 5. 5i, 5 in the I direction, 5 meters per second. So we know that the initial velocity here is 5 meters per second. Not just the initial velocity, it's a constant velocity because there's no acceleration there. To find the vertical velocity, which is the other component of the speed, we're going to need to use our old friend 2 vector. So when we reach B, we know that the displacement from the point of projection is -2. We know that the initial velocity is 8, as it was in the previous part of the question. We're trying to work out V. We know that A is -9.8. So we can use again V squared equals U squared plus 2AS. So V squared is 8 squared minus 19.6 multiplied by -2. So V squared is going to be 103.2. So V is going to be the square root of this, which is 10.2. And I'm going to put minus 10.2. And the reason for that is because I know at this point B, the velocity is negative, isn't it? I mean, when we square root the 103.2, we have the option of using plus or minus. We're going to use minus simply because it's traveling down. It's heading down towards B. Okay. So now we have our two velocities. We need to think of this as a right-angled triangle. Here is the kind of, that's the speed, that's the combined velocity from the two. We've got the horizontal velocity and we've got the vertical velocity. The horizontal velocity is 5, the vertical velocity is 10.2, and so what's the speed going to be? Using Pythagoras theorem, the square root of 10.2 squared plus 5 squared, and we'll work all this out. And we have 11.322 dot dot dot, and so the speed is 11 meters per second, correct to two significant figures. So now for part C, we're being asked the angle the velocity of the ball makes with the ground as it reaches B. Well, to find the angle, we're interested in this little right angle triangle again. Let's bring it down to play over here. Because this represents our speed. And if we're trying to work out what the angle is, we're just working out what this angle is. What's the angle made with the ground? So we have tan theta is 10.2 over 5. And so theta, remember to set a calculator in degrees. 64 degrees, correct to the nearest degree. So there we have it. Hopefully you can see that using vectors actually makes projectiles questions easier because we don't have to use sine and cosine for the angle. Thank you very much. See you later.